Welcome back to Smart Science. I have a few questions I'm going to be delivering today. So these questions were asked by one of my followers in the comment section. The first was that I provide an explanation, explain why phenylamine is a weaker base than ammonia. Phenylamine is a weaker base than ammonia. As I prepare to respond to this question, let me begin with the structure of phenylamine, which is NH2, and we all know that nitrogen has a lone pair. When I look at ammonia, nitrogen equally has a lone pair of electrons, and then the hydrogens are bonded to it in such a manner so that it develops what we call a trigonal pyramidal structure. Now, in alkalis or bases, base strength depends on the availability of the lone pair of electrons for donation. Availability of this lone pair for donation determines the base strength of all organic bases. So even if I'm to write my response, I'll say that base strength depends on availability of lone pairs of electrons on nitrogen, on the nitrogen atom for donation. That is what determines base strength. So in phenylamine, the lone pair of electrons on nitrogen, this one interacts with the benzene ring pi electrons. Because of this, it makes them unavailable, for donation than in ammonia. Thus, phenylamine becomes weaker base than ammonia. So from one of my followers who had requested me to talk about basicity, we shall discuss basicity of amines in form of availability of the lone pairs of electrons for donation. And on this very question, I would like to also talk about this. If I have methylamine, I have ethylamine, and I have a tertiary amine, we shall see that the more the alkyl groups are attached, the higher the positive inductive effect. And because of this positive inductive effect, the more available the lone pairs of electrons on nitrogen for donation. So because of this, we expect base strength to be increasing with increasing number of alkyl groups. So if I'm to put signs to show the level of basicity, the tertiary amine will be more basic than all the others, simply due to increased number of alkyl groups that pushes electrons towards the nitrogen atom, making the lone pair of electrons more available for donation. So the alkyl groups have a positive inductive effect, which I'm mentioning here, that makes our alkyl groups to become more available for donation. Lastly, I was also requested to talk about another question that this student of mine says that we also explain why when sodium carbonate was added to an aqueous solution of iron 3 sulfate, a brownie precipitate, and bubbles of a colorless gas were formed. I was requested to respond to this, and as I'm responding to this question, I would like to inform you that the chemistry we are going to be discussing here for iron 3 is similar for aluminium 3 and is also similar for chromium 3, simply because these ones undergo hydrolysis. And the hydrolysis that is talked about here is cationic hydrolysis. Cationic hydrolysis. So the equations we shall involve in this response are going to be mainly involving cations, because they are the ones that will undergo hydrolysis here. So as a response or a solution, we all agree that the iron 3 ions in the salt have a very small ionic radius with a very big charge. And because of this, they have a high charge density. Thus, because of that, they attract water molecules and undergo hydrolysis. Because they undergo hydrolysis, they end up forming iron 3 hydroxide, which is an insoluble brownie precipitate. And hydrogen ions that make the solution acidic. So we can decide to come up with an equation to represent this statement, where iron 3 ions in iron 3 sulfate are going to attract water molecules, and they are going to undergo hydrolysis to form iron 3 hydroxide, which is a solid, plus hydrogen ions, which are also aqueous. So we multiply water by 3, even the hydrogen ions by 3, in order to ensure that we have balanced the charges. Then the acid, it is now the acid. The acid is going to end up liberating. The acid liberates carbon dioxide gas from sodium carbonate. Forming effervescence. And this effervescence is what forms the bubbles of the colorless gas. So the observation we have been given, I think now we have explanations for both. The hydrogen ions which have been liberated from the above equation are going to react with the carbonate ions, which are aqueous, and this one gives us carbon dioxide, which is a gas, plus water, which is a liquid. Now we ensure that the equation is balancing. We shall multiply hydrogen ions by 2, and the rest will balance each other. Now, before we depart, we have to come up with an overall equation for learners who would prefer writing a single equation to eliminate equation number 1 and equation number 2. In case you want that, take the hydrogen ions in both equations to represent electrons when we are balancing ionic equations or half equations. So the number of hydrogen ions in the first equation will be used to multiply the second equation, and the number of hydrogen ions in the second equation are going to be used to multiply the first equation. So that in our addition, the hydrogen ions will end up cancelling simply because they are on opposite ends and they are equal in number. So in my overall equation, I'll have 2 iron 3 ions, which are aqueous. These ones are combining with the following. We would have gotten 6 water molecules, and here we have 3. Since water molecules are the same but on opposite sides of both equations, we shall subtract off, and where the excess lies is where we shall maintain the water. So we shall realize that we are maintaining water on the reactant side, and instead of 6, we remain with a balance of only 3. So plus 3 water molecules, which is aqueous, plus 3 carbonate ions coming from sodium carbonate. This one will give us 2 iron 3 hydroxide, which is a solid, plus 3 carbon dioxide, which is a gas. So this equation, when written, can replace equation number 1, and it can also replace equation number 2. So you describe like we've done here, you also describe like we've done here, and you come up with only a single equation of how the solution of iron 3 sulfate can react with sodium carbonate solution. So that is the inorganic chemistry that I was requested to upload a video on from one of my viewers. Thank you for maintaining the following, and please continue commenting. In case of any concern or any question, pass through the comment section of the video. I'll see it and I'll be able to respond to your concern. For those who have my personal numbers, you can still contact me over WhatsApp, and my WhatsApp number is 0705 5339 and 01. For any immediate response or concern, contact me through this contact to ensure that we can keep on following smart science. This company is a little big for those who would prefer sporting wear. Still, you can contact the same number via Smart Science. We can deliver that. Thank you very much for following. I wish you the best.